is a body of mass m attached to a spring constant k oscillate on a smooth horizontal table. It has a speed when the spring is at natural length. The distance it moved on the table before it come to instantaneous rest. So for this application, okay, we have to find out the distance moved on the table before it come to instantaneous rest. We have to find out what is the distance. Okay, by using work energy theorem. We have to find out distance by using work energy theorem. Now let us consider first one diagram. This is, for suppose, a rigid support and this is a smooth horizontal surface. Now let us consider this is a one block. This block is attached to natural length of the spring. It is just attached to spring. This block is attached to spring. Now this is natural length, for suppose. For suppose this block to one side and release it. What happened? What you observe? This block is oscillating. This block is start oscillating. So now the question is, whenever this block is to one side and release, now this block is start oscillating. Now for suppose this is one particular this is instantaneous rest position. Instantaneous rest position means, for suppose this is extreme position, this is mean position, and this side one extreme position. This is, for suppose one more extreme position. Now this block oscillates to and fro. At this particular position, it is instantaneous rest. Means you observe now it's here the speed of the block is v at natural length. Now given question, it has a speed v when the spring is at natural length here, and this means this is mean position. At mean position the speed is v. This is extreme position. Extreme position, it is movement initial instantaneously rest. Now here to here how much distance we have to find out. For suppose this is x. Now what is the distance x by using work energy theorem? For suppose at any particular length, for suppose at any particular position, this is any particular position. At this particular position, what is the force acting on the block? The force acting on the block, for suppose this is a normal force, and the weight of the block is acting downward. So that weight acting downward, so this is mg, downward direction. And this side, so whenever this block is here, now this spring is extension. So for suppose this spring is extension, now in this case the force acting, that force is nothing but spring force. That spring force is towards mean position. You know this information, you know this concept each and every one. Now we have to find out what is the distance it moved on the table before it come to instantaneous rest by using work energy theorem. So first, what is the work energy theorem? From work energy theorem, what is the work energy theorem? Summation of work is equal to change in its kinetic energy. Summation of work is equal to change in its kinetic energy. So here first work done due to net force. What is the net force acting on the block? Here how many forces are there? First, upward direction, normal force, downward direction, mg, and towards mean position, spring force, that is kx. Okay. Now due to n and due to mg, the work done 0, because you know the block displaces horizontal direction. This force and this gravitational force are vertical direction. The angle between the displacement and force, normal force and gravitational force 90. Okay, normal force and displacement, gravitational force and displacement of the block is 90. So the work done due to normal force and work done due to gravitational force, that equal to 0. So here total work, sum of work done means work done due to normal force, work done due to gravitational force plus work done due to spring force equal to now taking its kinetic energy. Change in kinetic energy means here, whenever the block at mean position, here what energy? That energy is nothing but half mv square. The block of mass of the block is m, and here velocity v square. So here energy is half mv square. Whenever the block at extreme position, here instantaneously rest means velocity is 0. Here kinetic energy is 0. Here kinetic energy is half mv square. This is initial. This is for suppose final. What is the change in kinetic energy? Final minus initial. Final kinetic energy minus initial kinetic energy. This is 0. This is 0. Now only spring force is there. Now what is the spring force? For suppose when the block moves this direction, the spring force this direction. Okay. When the block moving this direction, for suppose the spring force this direction. So this is minus of spring force is equal to, now final kinetic energy 0 minus initial kinetic energy of mv square. Of mv square. What is the spring force? What is the work done? Energy stored in the spring here. Okay. Work done by the spring here. That formula of kx square. So that formula of kx square equal to minus half mv square. So this work is nothing but work done or energy stored in the spring, or work done by the spring. Work done by the spring equal to half kx square. This formula. That work is nothing but here half kx square minus minus gets cancelled. I want to measure x. So here 2 also cancel. So x is equal to, x square is equal to m divided by k into v square. From this one, x equal to square root of m by k into v. So this is the distance it moves on the table before it comes to instantaneous rest. Before it comes to instantaneous rest, x is equal to square root of m by k into v. So that is the distance. Okay, this is one of the important form. Thank you very much. A bullet of mass m is fired horizontally with velocity v, which strikes a wooden block of mass m suspended vertically. If the bullet is embedded in the block, the height h to which the system would rises. Now, this is the question. For this question, we can prove which height of the block rises. What is the height of the block rises by using work energy theorem. So from this question, now the answer is first. Let us consider this is a one rigid support. Now this rigid support take one thread. By using thread, for suppose if we suspended one block, this block mass is, for suppose capital M is the mass. The mass of this block is capital M. Okay. Next, bullet mass. For suppose this is the bullet mass, and this bullet mass is small m. And this bullet velocity before striking the block, for suppose v. Now the question is first one more application. The application is first, the bullet of mass m is fired horizontally. Now this bullet is fired horizontally with velocity v, which strikes a wooden block. This is a wooden block of mass capital M, suspended vertically. This block is suspended vertically. If the bullet is embedded in the block, means if the bullet is whenever it is penetrate. Okay, now it is penetrate. So due to the velocity of the bullet, this block also moving this direction, and whenever here, now first what is the velocity of the combination of a block and bullet? After embedded this bullet, what is the common velocity of the mass of the block and bullet? First we have to find out. After that, what? Due to the common velocity, it is oscillating like this. This is oscillating. This block is oscillating like this. Now this is the position of the block. Okay. Now at this position, the bullet and block both are common velocity. At this particular position, for suppose this is extreme position, here velocity 0. The combination Okay, the common velocity of this block and bullet is 0 at extreme position. Now we have to find out from what height it rises. It rises what height? It comes to rest. Okay, so once bullet of mass m is small m and bullet velocity before collision its velocity v, and here it is rest position. This block it is suspended vertically. Okay, it is rest position before collision. Now after embedded this bullet in the block, the height to which the system would rise, the total system bullet block mass system, how much height it rises, that is the question. By using work energy theorem, we can measure, we can find what is the height. Okay, first what is the common velocity at this position? At this position, that is nothing but this mean position, it is extreme position. At mean position, what is the velocity? First we have to find out. Now you know the law of conservation of linear momentum. From law of conservation of linear momentum. From law of conservation of linear momentum, what is the law of conservation of before collision at this particular at mean position? Before collision, momentum of the bullet is mv. Now this block momentum capital M into 0 because there is no velocity at this particular position. After collision, both are total mass of the bullet mass system, bullet block system is m plus m, and its common velocity for suppose vc. Vc for common velocity. So from this one, what is Vc value? That Vc equal to, we can write m divided by v divided by capital M plus small m. This is the common velocity of the bullet block system. Common velocity whenever this bullet passes inside wooden block or embedded wooden block. Now both having common velocity. Okay, that common velocity is equal to mv divided by m plus v. Now here you know at this particular position the common velocity of the bullet and block system Vc at this particular position. Now velocity is 0. You know according to from work energy theorem, you know summation of work is equal to change in its kinetic energy. Summation of work is equal to change in its kinetic energy. So here kinetic energy you know because mass you know, velocity you know. Here kinetic energy is 0 because velocity is 0. So change in kinetic energy you know. Next, what are the forces acting on the bullet? Gravitational force. This bullet and block mass system, gravitational force acting downward. That force is mg, m plus small m into z. This is the total mass of the system. After embedded the bullet. Okay, the total mass of the system m plus small m into z. So this is m plus small m is total mass. It is gravity. So this is the gravitational force downward. Okay, and attention this one. So what is the net force acting on the block? The net force acting on the block is gravitational force downward. Okay, so this gravitational force affect only vertical direction. So this block here to here, now the displacement in the horizontal direction there is no effect of gravitational force because gravitational force downward, the displacement is horizontal direction. Now angle between these two is 90 degrees. So due to horizontal direction gravity effect 0. Work done due to gravity along horizontal direction 0. So this gravitational force affect only vertical direction. So that's why only this direction gravitational force affect this direction. This direction because here to here displacement both x direction and y direction, but x direction there is no gravitational effect. Okay, because the work but x direction the work done due to gravitational force 0, along y direction only gravitational force is there. Now according to from work energy theorem, summation of W is equal to delta K. That means work done only due to gravity equal to change in its kinetic energy. Means final kinetic energy here 0 and initial kinetic energy initial kinetic energy is half. Now what is the total mass of the system? M plus m into common velocity square. Now work done by gravity is nothing but that is this gravitational force downward, the height is upward direction vertically, so it is opposite to the direction of motion along the vertical direction. So that's why here minus, now total mass of the system m plus m z and that height is h equal to, now it is minus of m plus m. What is the common velocity? Common velocity is mv divided by m plus m whole square. This is the common velocity. Now from this one, m plus m gets cancelled, minus gets cancelled. I want to measure only what height to which the system will rise. So h we have to find out. So that h is equal to 1 by 2z. This d take this side, 1 by 2z. Now we can write mv divided by m plus m whole square. So this is the height of the system which we rise. Height of the system which we rise. So this is one of the application of work energy theorem. This is also important. Okay. Thank you very much everyone.